We are Team 11 and today we're gonna look at the paper, look at the first sentence, position bias in question answering. Let's start with the problem. This paper hypothesizes that when the distribution of the answer positions is highly skewed in the training set, in QA models, predicting answers as positions can learn false positional cues and fail to give answers in different positions. For that, let's take a look at the picture on the right hand side. This picture shows an example of position bias. BERT trained on the dataset with a skewed answer position distribution provides wrong predictions, bias to the specific sentence position. Next, let's talk about methods and approach. First, this paper makes 3 contributions. First of all, we define position bias in extractive question answering and show how it affects extractive QA models in general. Second, we look at the reasons why the bias models failed and demonstrate how positions might behave as fictitious biases. Third, we demonstrate how the prior distribution of the response positions enables us to construct models that are positionally unbiased. Let's look at the approach in more detail. First, we demonstrate the presence of position bias using bias training sets sampled from SQuAD, which is the data set we are going to use, and my teammate is going to talk more about it in the next section. Second, for examining the reasons for the failure, we visualize position bias with BERT trained on SQuAD train, the original dataset, SQuAD K1 train, the dataset which is focused on the first sentences only, and BERT without fine-tuning. And lastly, to debias the models by using prior distribution of answer positions. To do that, we use entropy regularization and bias ensembling. Let's talk about the last part more in detail. In the baseline, we use 2 methods, randomized position and entropy regularization. But to get even better results, we use bias ensemble with answer prior. Regarding the word level answer prior, it means that given the training set having n examples having n answers, we compute the word level answer prior at position I over the training set. We also use the sentence level answer prior, which dynamically changes depending on the sentence boundaries of each sample. And we should also mention that both word level and sentence level answer priors are experimented with 2 bias ensemble methods, product of expert with bias, which is called bias product, and learning mixing of 2 log probabilities, learned mixing. And you can see the respective pictures on the right hand side.
We used 5 synthetic datasets. As can be seen from the name, each one is a biased dataset where the answer lies in the given position in the table. All of them together form the SQuAD dataset, which consists of 87,599 data. Some of the experiments were done explicitly to show the existence of bias. For these experiments, we had 3 more datasets, which authors call SQuAD sampling, SQuAD plus first sentence, and SQuAD plus shuffle sentence. The first one sampled the same amount of data as SQuAD k equal 1 case from the whole dataset. The second one truncates each context up to the first sentence, and the last one shuffles the sentences in the biased dataset. Now we move to replication results. I'll talk about experiment settings. We referred to author's code for most of the replication approach. Some of the problems we faced during replicating include some bugs in the code, lack of some datasets and models. We had to code some scripts to get datasets used in detecting bias. For that, we used an NLTK library to process text data. Let's talk about experiment settings. As we mentioned in previous slides, for all of the experiments, we used SQuAD dataset and its subsets. We used BERT model to be more precise, Bayes model, which has 12 layers in encoder as a pre-trained model. Optimizer and learning rate scheduler are ADAM-W and linear scheduler respectively, with an initial learning rate of 3 times 10 to the minus 5. Batch size is 12 for both fine-tuning and evaluation. Training was done for 2 epochs for every experiment. Lastly, evaluation metrics are exact matching and F1 scores. Next, we move to replication results.
We first replicated the part where they demonstrate the existence of position bias using bias training sets. Given that the first data set where all answers are in the first sentences was given in their GitHub repo, we trained BERT model on this data set and evaluated on the development set. Note that it has around 28,000 samples out of 88,000. For a fair comparison, we also randomly sample examples from the original training set and make another dataset, which is called squad train sample, which has the same number of examples with squad train k is equal to 1. As shown in the tables, our results are quite similar to the results of the paper. In both cases, we can see that performance of the BERT model drops significantly compared to the BERT trained on the full squad dataset and randomly sampled dataset. In both tables, the bias dataset has exact match around 31, but full squad and sample squad have around 81. To understand the cause of position bias, the paper has done 2 more experiments with per-process squad dataset. We have done that too. First, we shorten each patches up to the first sentence and get the following datasets. For the second one, we shuffle the order of the sentences and got a new dataset. As we can see from the result, in both cases, most performance is recovered. In the second part of the experiment, they introduced solutions for BERT to prevent models from learning a direct correlation between word position. They are randomized position and entropy regularization. For BERT, we did the sentence level answer prior with 2 bias ensemble methods, bias product and learned mixing. We first trained BERT on squad train k is equal to 1 with the biasing methods and evaluated them on squad development set and squad development set whose answers in the first sentences and another subset of this development set whose answers do not appear in the first sentence but in other sentences. The results demonstrate that the biasing methods increase exact match for our biased dataset. Here are the results of training BERT with our debiasing methods on the full training set squad. Here answers are spread in all sentence positions. These results show that when the positional distribution doesn't change much, then our methods work well. As you may see from the tables, the exact match is around 80 for both baseline and sentence level tasks. In the third part of the experiment, they construct 4 squad train dataset based on sentence position of answers for k is equal to 2, 3, 4, and greater than 4. We did the experiments for simple BERT, bias product, and learned mixing, and evaluated on squad development set. As seen from the tables, BERT model suffers from position bias in every sentence position, while the learned mixing method successfully resolved the bias. To complete the replication, we are planning to replicate the results of experiments for the other models. They are BiDef and ExcelNet. So far, all the experiments we have done is based on squad dataset. To complete the replication, we are planning to test the effects of the biasing methods on 2 more datasets, new question answer and natural questions.
Our plan for improvement is as follows. First of all, we'd like to look at the groups of question answer classes for different values of k. We'd like to find the relationship between the amount of bias that's present in the model and the count of groups. So basically, we'd like to see if we have a lot of groups of different values of k for the questions, would it be able to help against bias? Would BERT model would be able to overcome the bias? And we'd like to see if there is some count of group that would make bias negligible. Secondly, we'd like to see how prepending random sentences in the beginning of the passage would affect the performance of the model. Obviously, this modification would be moving the value of k along the passage, but because it's randomly generated sentences, we don't know if this will be helpful. So we'd like to test this hypothesis. Then we'd like to experiment with different models like BERT, large uncased, and try to tweak the model by tuning hyperparameters or by changing the structure of the model itself. This is self-explanatory. Then we'd like to experiment with some more data sets like Wiki QA, which is also self-explanatory. And we'd like to try to undermine the limitation brought about by the authors regarding the usage of multi-paragraph length context. In the paper itself, authors used only one paragraph length context, but we'd like to see how the model is gonna work with different length paragraph context.